I was on the internet some times ago and I discovered that there are some problems in mathematics that has never been solved. One of those problems has to do with prime factors of very large numbers. Now, with respect to that, I decided to work on prime numbers. And as a result of my work, I wrote this book to solve these problems of prime numbers. Now, the basic explanation of the book is as follows. Basically, I gave the book a name, Prime Factor Configuration. Now, the first basic chapter of this book deals with systematic way of finding any prime number or verifying any prime number. In mathematics, prime numbers are a unique set of numbers. When I say that they are a unique set of numbers, all natural numbers can be expressed in terms of its prime factors. And after taking a careful study of prime numbers, there are certain facts I established. That prime is an attribute of natural numbers. Only natural numbers can be prime numbers. Now, this means that negative numbers, irrational numbers, fractions, complex numbers cannot be prime numbers. Now, this gives us a point of concentration, natural numbers. Now, another fact that was established from my studies, the number 1 is not a prime number. Mathematics have always shown us that. The number 1 is not a prime number. Now, this is because it has only one factor. Every prime number has 2 different factors according to definition of prime numbers. But 1 has only one factor, and because of that, 1 is not considered as a prime number. The other fact there is that just like natural numbers, they were ordered from 0, 1, 2, 3, 4. They were ordered from small to big. Prime numbers, they are also ordered from small to big. Another important fact there is that perfect squares, they are not prime numbers. There is no perfect square that is a prime number. Another important fact there is that the number 2 as a number, that is the only even prime number we have. Every other even number are not prime, but only 2 is the only even prime number we have. Now, taking these facts into consideration with other mathematical principles, I came up with the following algorithm for finding and verifying prime numbers. Now, in this book, I cited a case study given a number x. Verify whether x is a prime number and find all the prime numbers less than x. The solution step is as follows. The first step, the first step here was basically divided into two. These two pathways. These two pathways means that I can go through these systematic steps and continue from step 2. And I can go through this systematic step and continue from step 2. What am I trying to say? No. Each of these pathways have a different approach. Here, for example, the approach started that if the number in question that we want to verify whether it is a prime number first, if you divide it by 2 and is equal to 1, then the number is a prime number. But if you divide it by 2 and it is not equal to 1, then you proceed to the next step, that is step 1b. Divide the number by 3, if it is equal to 1, it is a prime number. But if it is not equal to 1, you proceed to step 1c. You divide the number by 5, if it is equal to 1, it is a prime number. But if it is not equal to 1, then you proceed to this step, step 1d. You divide the number by 7, it is a prime number. If it is equal to 1, it is a prime number. But if it is not equal to 1, then we move over to the second step, that is step 2. Now, this step 1 that is divided into 4 series here is brought very close into one basic step in this other pathway. I establish it as a set. Let a definite set I, that is a set I invented, that is a set I invented. The definite set I contains number 2, 3, 5, 7. I labeled this set, the name, I named it. The label is I is equal to this. I named it the set of prime constants. Why I invented this prime constant is that they are specific group of prime numbers that is less than 10. All prime numbers less than 10, I referred to them as prime constants because of their importance in this algorithm. Even when you look at the other pathway, they are what was used in establishing each step, each sub-step in this step 1. They are what was used in establishing each sub-step in this step 1. 2, 3, 5, 7, those are the prime constants. That is what I call them. Now, having known this set, I is equal to this. If x is an element of I, then x is prime. But if x is not an element of prime, then we proceed to step 2. Now, step 2. Now, the step 2. The step 2, I invented another set. Let a set M contain element y such that 2 is equal to or less than y and y is equal to or less than x over 2. X is the number in question we are trying to verify. Now, y is natural numbers. So we are talking about natural numbers ranging from 2 to half of x. Now, having known that, the square root of x is an element of m, then x is not a prime number. That means that x is a perfect square. If the square root of m is an if the square root of x is an element of m, here for example, m contain only natural numbers. So if the square root of x will give us a natural number, that makes x a perfect square. And if x is a perfect square, x is not a prime number. But if square root of x is not an element of m, then we proceed to step 3. That is the step 3 now. Now in this step 3, we set up a modular table for this binary operation, a operation b, as a times b, multiplication. Now, the binary operation we are setting up now is for k operation t, which is k times t. Now, what is k? K is the set containing w. 2 less than or equal to w, w less than or equal to x over 2. X is the number we are trying to verify in. W, they are natural numbers. T is equal to I union A. Remember, I is set of prime constants that I invented. Then A lot of set differences. A is expressed in terms of a lot of set differences. The set difference between C and D started it. Then this involving set difference between C and D, E. Set difference between the whole of this and F. Set difference between the whole of this and G. Set difference between the whole of this and H. And that result will give you A. Now, what is C, D, E, F, G, H? Look at them here. Here, C I define as a set containing element Z such that 11 is less than or equal to Z. Z is less than or equal to x over 2. They say that Z is a natural number. So we are talking about natural numbers ranging from 11 to half of that number. D contains element R such that 11 is less than or equal to R and R is less than or equal to x over 2. That is half of that number. Now R in question, they are even numbers. E contains element X such that 11 is less than or equal to x and x is less than or equal to x over 2. X is multiples of 3. F defined by the set T such that 11 is less than or equal to T and T is less than or equal to half of x. T is multiples of 5. G containing element U such that 11 is less than or equal to U, U is less than or equal to x over 2, U is multiple of 7. And H containing element Z such that 11 is less than or equal to Z, containing element J such that 11 is less than or equal to J and J is less than or equal to x over 2. J is perfect square. Now, having defined this and having established your K and your T, the next thing is you develop the modular table. When I say a modular table, I'll give an illustration. The one I used for illustration looked like this. And what is this modular table all about? That is a modular table of K against T. K against T. And that is the kind of modular table. The binary operation involved is multiplication. Now, having done this, having established this modular table, the next step is to establish a set P such that contains element n such that 2 is less than or equal to n, then n is less than or equal to x from 2 to that number x. N is integers, whole numbers. All the whole numbers ranging from 2 to x. That is what is contained in element P. And B containing element containing element V, such that V is equal to the product of K and F, K operation T. Having established this modular table, the next thing is to set up a set P containing element N such that 2 is less than or equal to N and N is less than or equal to X. N is integers, whole numbers ranging from 2 to X. Then after that, we establish another set B containing element V such that V is equal to K operation T. That means all the products that we have formed in this modular table, that is K operation T. Then after that, you set up another set S. This X is the set difference between P and B. Now we say that once we set up this set X, that this set X will contain all the prime numbers less than or equal to X. That is, if X is a prime number, you find it in the as an element of X. If X is not a prime number, you will not find it there. Thus, if X is an element of X, then X is a prime number. Thus, if X is an element of S, then X is a prime number. In the book, I try to explain this, the symbol that was used, so that people doesn't get confused. That is the set difference. That stroke is the set difference symbol. So in summary, this logarithm was able to give us prime numbers, and the logarithm was also able to verify whether that X is a prime number. Now we have an illustration, a typical illustration here, taking 47 as a typical illustration here. 47. Identify the prime numbers less than or equal to 47 and verify whether 47 is a prime number. The logarithm can be able to do it. As it can do it for a small number, it can also do it for a very large number. From there, once the number is made known, you can establish your C, D, E, F, G, H. Once you know that, you know your A. Once you know your A, I is constant. That is the set of prime constants. The set of prime constants that I established here formally. Now, once I have my T and my K, the next thing is to generate the modular table. If I generate the modular table between T and K, this one is for K, this one is for T. Now, from there I can be able to establish B. B, they are the factors that we have produced, starting from this line down to the last line. They are the factors that were produced. Then B, P, for example, is a constant integer ranging from 2 to that particular 47. 2 is less than or equal to N, and N is less than or equal to 47. Once I establish B and P following the same procedure I explained formally, the next thing is to find the set S that contains all the prime numbers less than or equal to 47, which is the set difference between P and B. Once that is done, the set of X will contain all the prime numbers less than or equal to 47. And since 47 is an element of S, then 47 is a prime number, and that is a verification process. In the chapter 2 of this book, we saw a logarithm for identifying prime factors of a number, no matter how the number, whether it is a small number or a very large number. From chapter 1, we recall the sets that were established. I is very important. The set of prime constants. K is still what it is. T is I union A. To produce the prime factors of X, you say you generate a modular table. Generate a modular table. K operation X. We know what S is. That is S. That is the set of all prime numbers less than or equal to the number in question. X is P, set difference between P and B. Now, when this modular table is established, you say that the values of X that will produce X on the table, that will give a product of X on the table. What does it mean? Look at the S. The values of S, look at the S here. This one is the K. The values here that will produce X on the table as a product. So any place I find the product here, I will say, okay, if the product in question, let's say for example we're talking about 50. Okay, 50 in question, what value of X gave us, of S gave us 50? 5. That is a prime factor. The values of S that will give X, that will produce X on the table, will represent the prime factors of X. If the number X is not produced on the table, then X is a prime factor. And its factors are itself and 1, with itself as the only prime factor, because 1 is not a prime number. Now, I give illustration. Finding prime factors of 48. I establish my K, then I establish my X, my P, B, and my X. Then after that, the modular table for K against S. Now, when you look at it, you find that when you look at it, you find that the values of S that will give 48 product on the table represents the prime factors of 48. So on S, we go and check. This one gave us 48 here. 2 is a prime factor of 48. 3 gave us 48 here. 3 is also a prime factor of 48. 5, no 48. 7, no 48. 11, no 48. This other one, 13, no 48. 17, no 48. 19, no 48. 23, no 48. So you find out that the only prime factors of 48, they are 2 and 3. Now, with respect to that, 48 can be expressed in terms of 2 and 3. Knowing that the prime factors of 48 are 2 and 3, you can go ahead and express 48 in terms of 2 and 3. Yeah, I'm very happy to share these wonderful facts with the whole world.